Here I am.
Well, on the coast.
Okay, well, it's 7:31. Shall we get things started?
Sure.
Sure.
Want some more join us, but go ahead.
All right, well, everybody, welcome to our May edition of our Chester County Astronomical Society meeting, and welcome all, especially those who are tuning in from other clubs on YouTube and the other formats that we've been using. That's been great having so many guests and people from other clubs joining us and sharing the wonderful program that Bruce has put together for us this year. We're going to be doing things a little bit differently tonight because John Conrad has very kindly volunteered to give us an update he'd like to give us on the latest on the launch of the James Webb Space Telescope. But he said he wanted about 5 or 10 minutes for that. I'll let you decide, Don, whether or not we have time to do our usual stellarium and other presentations or what's up for the month. So if you think that we can get away with it, why don't we just go right to that?
So why don't I have John start?
Absolutely. John, you with us?
Yeah, I am. Let me see if I can share my screen here.
Yep, it's working.
Yes, we got it.
Yeah, we see it.
Good.
All right, I'm going to mute.
All right. So I'll try to take just a few minutes here. An opportunity presented itself, and so I decided to take advantage of it. And that was that the media, not just the international or the US, but the international media was invited to a briefing that happened this afternoon. And without anybody asking me, I'll tell you that I have no idea how I was able to attend, but I did. And it was a virtual room filled with reporters from here and there. And it was these fine folks from the James Webb program that you see listed here. I hope you can see that list of 5 people. Everybody seeing that?
Yep, we're seeing it.
Yeah,
Yep.
we do.
Okay,
Yep,
good.
we see you.
Yes, yes.
So, I mean, as much as anything, I wanted to go because this is quite a group. Not only does it have NASA's top people, maybe 1 or 2 of them has talked to the ambassadors before, and this was not an opportunity for ambassadors. It's just something I happened to get an invite to, and then I was able to sneak in like I was in the media. At any rate, it didn't just have the NASA guys, it had the top guy from Northrop Grumman. And so I wanted to hear what the contractor that built the spacecraft, this wonderful telescope, had to say, as well as the top people from NASA in what they build as the final media briefing before it gets shipped to the launch site. So without further ado, if this works, we'll go to the next slide. And for some reason, it is not, there we go. Okay.
Yep, we got it.
So I only have 5-10 minutes, so I'm gonna go quick. They updated us with everybody crossing their fingers that nothing's changed the launch date. It's still Halloween. And it's still, as you had heard, from French Guiana. And the good news to me was to hear about the depth of testing that this thing has gone through with simulators that allow it to test all of the operations of everything as the segments get folded out and the telescope gets set up with the not just the primary, but the secondary being erected and so on. All this has been done with very high fidelity simulators. 2 things in particular which are interesting to me, since this is going to be a focal plane, all the focal planes, I should say, all the elements of the telescope, as well as, of course, all of the instruments are being brought down to very low temperatures. And so they had to test all this and really, whatever the opposite of bake is, put it into a cryo chamber for, I think, well over a month. And they've done that. They did it in order to verify that at those low temperatures, close to 0, that the shape of the segments, once they were all folded out, would be the correct shape so that they wouldn't run into the problem that Hubble had. And one of the neatest things they talked about with the simulators was they were able to put the entire spacecraft with all of the sun shields pulled out and stretched out into a chamber, and then not just simulate, but actually fire the equivalent of micrometeorites at it in order to give it a cumulative load of many, many years to see what would happen to the surface of the telescope, as well as to the very thin mylar of these sun shields. And indeed, as you would expect, there was some pock marks, but nothing broke. Nothing was degraded to any great extent. And so that was really good news to go through that, because it will experience the micrometeorite environment. It's still in Los Angeles. For those of you who follow companies that do space stuff, TRW is really the contractor. And for the young people that have never heard of them, they were a star in the 70s and 80s and into the 90s for really complex spacecraft. JPL used them a lot and so on. And that's actually their facilities, which were consolidated into the Northrop Grumman company that are responsible for this. And so that's where it is still after all the testing. It's getting packaged right now for shipment. And I emphasize the word ship because that's how it gets to the launch site on the eastern side of South America by going through the Panama Canal. So that's coming up yet. The question was addressed for the press, going back in time, why do we need this new telescope? And so they talked about a particularly interesting finding with Hubble when it looked deep, that they just couldn't see the earliest galaxies. And Spitzer, which you may remember from the talks recently, is able to see with greater look back times, but not with very good resolution. And so dim things like distant galaxies didn't show up. And so they needed something that combined resolution and better stretch into the infrared. And so it's going to be able to see back farther and earlier. It also sees near better than anything, including Hubble, and especially things like being able to see, if you will, nearby exoplanet systems in our galaxy. And in the cases where we've been able to see lanes of forming planetary systems before, but never the planets, we expect now to be able to actually look at these protoplanetary disks and not only see the stars, but see the planets form and see the atmospheres of these exoplanets within the solar system. And I think this is exciting. Their early observations are going to look at some of Jupiter's moons with better resolution than ever, and Uranus and Neptune and the dwarf planets in the Kuiper Belt, as well as other Kuiper Belt objects and so on. And then finally, again, this is addressing the question of why do we need this new telescope? Well, just like with Hubble, in astronomy, you guys know as well as anybody, the questions keep coming up because we by far don't have all the answers. And in just the last few years, these few things at the bottom here have been called into question.
Funny
as
because
to
these are horrible. These.
Can you hear me?
Can you hear me? Hello?
We can hear you. Someone is off.
Okay.
Someone needs to mute.
Yeah. Okay. Anyway, so these are three key things that we expect with the Webb's deep look that they'll be able to see, and with its infrared to be able to look into our galaxy center with better resolution, as well as into other galaxy centers, and look for these supermassive black holes. And the neutron star collisions, which have become pretty well known from the gravity wave situation, we suspect are involved in the formation of many elements. And this will allow a look at that for the spectroscopic assessment of that. And then finally, I just want to note that while the reporters were asking questions, I kept waiting for one, and you can probably guess which question. Dave can guess because he asked me the last time we talked. and everybody finally gets to this one. And that's, since this thing is, close to 1,000,000 miles away, can we service it if it doesn't all work perfectly? And so we all waited to hear the answer because the Northrop Grumman guy was there. And the first thing they said was the Webb was not designed to be serviced like Hubble, which we already knew, and it's too bad, I think. But they went on and said it has been built so that it can be refueled. And I mean, it's the fuel that will determine its lifetime eventually, in terms of having, the cryogenic capability and the station keeping capability in its halo orbit. So I think it's kind of interesting. I'd like to know the evolution of that decision. They may have very well modified something as they got pressed to make sure that, since we certainly can fly out to the L2 Lagrange point, that at least we could send something out, and they put in a capability, I don't know, some kind of a gas cap to open and refuel it if needed, but they still can't service it. Anyway, we'll see how it goes. And I thought you'd all be interested in hearing that update. So that's it.
Thanks, John.
Thank you.
You're welcome.
Good info, thanks. We'll do a look at the night sky, Bruce.
Sure, yeah.
Okay, let me share my screen. And I'm going to do things just a little bit different. Usually we focus on constellations. So I thought tonight we'll look at a couple planetary and solar system things. So this is 24 after 8 tomorrow night. Today's 11th, that's going to be on the 12th. The moon, this is going to be a real observing challenge. This is only like a day and a half old moon, not even that, because new moon was this afternoon at 2 o'clock or so. So to see a moon with that thin a crescent is a real challenge. It's just the only part that's lit is right down here. You can barely see it. But if you can find it, there's Venus right next to it. So I'm going to center on the moon. We're going to go up to a day later. If I can get to center on the moon, it should have, but now. So on Thursday, it's going to be right next to Mercury. And you can see now there's a little bit more lit. So Thursday is definitely doable. If we have clear skies, this should be a really cool opportunity for taking photos. So now if I back up to a point, then it just shows the whole lit moon, this is the simulation. This is actually accurate. The moon will have just the very, very edge lit. And it looks really cool on telescope binoculars when it's that new. So that'll be about a two and a partial day old moon. Then we go the next day, and the moon is approaching a little later in the evening. It's approaching Mars. Oh, where'd my moon go? There's my moon. Moon and Mars. Let me center on the moon. I'll go up an hour later. Getting a little bit closer, and I think by the time it sets, though, it's just below the horizon now. But if we go another day, let me center on the moon again. We go the next day, the moon is right in Gemini. We'll go one after that. Let me check the date. On the 17th. On the 17th, this would be a really cool sight. The moon is very close to the Beehive cluster. I have to zoom in here to have the Beehive cluster show up. There it is. So there's a photo opportunity. I can't get the moon to show up and the Beehive at the same time here, because if I zoom out, the Beehive disappears. That's just a limitation of the program. But the Beehive is an amazing, amazing cluster of binoculars. So probably if you have the best thing to take a picture of this, because they're so far apart, would be a digital camera, DSLR. You can get both these in one frame, because any telescope, it'll be too big a field of view, I think. But just to see the Beehive in binoculars, it's a nice thing to do. So those are the solar system things that are going on. Now there is one other. I'm not even going to bother simulate it, but On the 26th, there is a total lunar eclipse in progress just as the moon sets early in the morning, the pre-dawn sky. I simulated it and there's nothing to see, so I'm not going to go and show you now. So, but there's lots of great other things to see in the sky. What else? Oh, on the 18th, let's go to the 18th, center of the moon. And again, we can't see it in the simulation here, but on the 18th, one of our favorites, the lunar X and the lunar V are visible at 8 o'clock in the evening. Okay, so I'll send a reminder out about that because the lunar X and lunar V are really fun to look at. So, any questions? I'm going to focus on planetary stuff this month just for a change. Any questions on anything?
So if the lunar X is going to be up, Don, are we going to have a repeat of your famous lunar X party?
Well, that's a good question. What is the 18th? Well, let's see. 18th, that is voting day.
Okay, Tuesday.
A Tuesday.
Yeah, primary.
I don't know because I know Barb and I are poll workers, so we're probably not going to be able to do it here at home.
Ah, too bad.
We volunteer at the polls. We're the people that come in and yell at people to stand in line. So, okay. Any other questions on anything? We're up to over 30 now, over 30 people now watching, so that's good.
Good.
So Bruce, I guess we have to go next is Laura to come on, huh?
Okay,
Okay.
great. So, good evening, everyone. As most of you probably know, this I think is going to be our last official meeting for the spring, and we'll probably break until September. And so tonight have as a guest speaker, Dr. Laura Kerber. Laura is a research scientist at JPL. She studies planetary geology with a focus really in physical volcanology, extraterrestrial cave environments, and the ancient Martian climate. Laura has 2 master's degrees in geology and fluid mechanics, as well as a PhD in geology from Brown. And she enjoys doing remote sensing, field work, and modeling, and works really on studying the interaction between planetary atmospheres and planetary geology with a focus primarily on the moon, Mars, and Mercury. So she is currently the deputy project scientist for the Mars Odyssey mission, and she is also the principal investigator of the Moondiver Discover mission, and that is what she's going to speak to us about tonight. So Laura, it's a real pleasure to welcome you to Chester County Astronomical Society.
Thank you very much. And I got to see that shirt again. Who was wearing that amazing shirt? Yeah, Dave. Wow.
Yeah.
I didn't even know about that shirt at all. I just looked it up on the internet. That's so amazing. I have to buy one for myself.
We can send one to you.
So I'm going to, let's see, I'm going to share my screen now. I'm actually on here in 2 different instances, so hopefully that won't be too confusing.
It's working.
Okay, good. Let's see.
Good.
Okay, now you can see it in full screen, I hope. And can you hear me okay?
Yes.
Yes,
Yeah.
working well.
Okay, great. So today I'm going to talk to you about this mission Moondiver. I guess they call it a mission concept because it's not a full mission yet. And I'm going to tell you a little bit about the mission itself and its goals and where it wants to go. And then a little bit about the mission formulation process, which I also think is an interesting process. That if you have an idea for a mission that you want NASA to do, then how does it actually get to be a mission eventually in the future? So this all started back in about 2009, 2010, and that's when there was a spacecraft, Japanese spacecraft called Selene or Kaguya, and it discovered these several mysterious holes in the moon. And the guy that did this, Junichi Hariyama, is a friend of mine, and it was very hard. He had a bunch of students. He was just sure that there had to be some holes in the moon. But if you want to find a hole, especially this data wasn't super high resolution, you had to go through very carefully and distinguish holes from craters. And that takes a lot of time. You have to look at the hole throughout different illuminations throughout the day and discover, is this something that has a bottom? Can we see the bottom of it? Is it have an overhang, etc.? So the pictures you're looking at here are of a particular hole called the Mare Tranquillitatis hole. And this is actually taken by the spacecraft, the Lunar Reconnaissance Orbiter, which is American spacecraft, has a much better camera. As soon as the Japanese spacecraft found the holes, then they were targeted by this beautiful camera, and they took pictures of it about 50 centimeters per pixel. And so they were able to take pictures of it different times of day, and they were able to see down to the bottom of the hole, and actually by kind of slewing off nadir, they could see underneath the overhang, which is pretty amazing. So when this first was discovered, it got a lot of press. You know, there's a hole in the moon, and there's hidden tunnels below the moon, and you know, TED talks about it, and this guy on YouTube actually sang a country song, "How's About Them Holes in the Moon?" And people started thinking about, wow, if there really is this big hole in the moon, one of the big reasons that could be there is if there's a big lava tube below. And people had done calculations about how large these lava tubes could potentially be, and realizing under the low gravity environment of the moon, and you don't have too many earthquakes, that you could have enormous lava tubes, and you could really fit a lot down there, like an entire city. And if you had people down there, the roof of the lava tube would be protecting you from radiation. It's actually the same temperature all year round down there, which is actually kind of a nice 15 degrees C. And so it could provide a lot of nice things that astronauts might want. So people thought, oh, we could put a future moon base there. We're totally going back. Scouting lunar caverns is a possible site for a moon base. Then there's the people that, in addition to thinking about what could we put down there, they started thinking about what could already be down there. So we had all these kind of fringe conspiracy theorists, you know, like, might we find a monolith down there at the bottom of this cave? Some people thought the moon is hollow, and there's this whole conspiracy theory that the moon is like hollowed out and it's a spacecraft inside, and at some point they're going to decide to fly it away. So this is the idea of the hollow moon. So this hole would be an entrance into the hollow moon. But what I always say is NASA definitely checked to make sure to see if the moon was hollow, and it's not hollow, so that's too bad. So what is this hole like? It is enormous. I just superposed a football field from a local high school onto this hole. That's about how it's about 100 meters across. And then I superposed the hole onto the JPL campus, which you guys really should have a field trip and come visit. It swallows our entire cafeteria and outside eating area, and you know, could swallow basically our entire parking lot. And then how deep is it? I tried to find a bunch of buildings that would fit inside this pit. The Big Ben fits inside, the Saturn V fits inside, the SLS Block 2 rocket fits, the whole thing fits inside. You could launch it out of there like a missile silo. And I think there is maybe like 20 giraffes if you stack them all on top of each other. In meters, it's about 125 meters deep, which is over 400 feet. So it's a pretty enormous hole. And just to give you a little sense of how big that is, if you see very small across the far side of this pit is my friend in the yellow. And then this hole, the one on the moon, is twice as deep and about 3 times as wide as this hole that you're looking at. So there I was. I saw this beautiful pit. I sort of started getting into it around 2014, 2015, as they started getting better and better pictures of these holes in the moon. And I thought, wow, it'd be really amazing to explore this pit. But it's also really challenging because a normal rover, there's no way that you could explore this pit with a normal rover. How would you get into the edge of the pit? How would you get down inside the pit? This was unknown. So one day I was hanging out at lunch and I met this guy, Ethan Esnes, and he happened to have an extreme terrain rover, which he was looking for an application for. And this is a two-wheeled rover. It's called the axle rover because it's a giant axle. And then you shelter all of the instruments inside of this payload bay that swivels around kind of like a lazy Susan. So anything you want to look at, you take the instrument out of this blue door and then you swivel around the next instrument, look at the same spot, and it protects all of those instruments from falling rocks and dust and everything else that you would encounter as you're extreme terrain rappelling down some cliff face. So he had thought about this for Mars. He had thought about it for the permanently shadowed regions of the moon. He had heard about these pits and thought, yeah, that, I bet my rover would be really good for that. But once we met each other, it was, we were very excited. Oh yeah, this is something that we could actually do. And I started working with him and his team. So here's a prototype of the axle rover that they built, and they were demonstrating it in a quarry. And so it can go down and up. It actually, one of the key things about it is that in the middle there, you see it keeps its spool. So it spools its own tether out as it goes, kind of like a vacuum cleaner. So that helps it not get snagged, and it helps the tether not drag too much across the surface, which is pretty rough. And then here's a little video showing how the instruments come out of that payload bay as they spin around. And they have cameras actually built into the body of the rover, and then this nice tether and a spool that are at the center of the rover that rotate independently. So you can sit in one spot, and you have the wheels on the outside that rotate independently as well. So the first thing I decided to do is, okay, I want to do a mission. I've never done a mission before. I have a friend whose mission was recently selected, and it took him from the first thought that he had about the mission until it finally got selected, something like 30 years. So I was thinking, all right, I gotta get started right now. I've been at JPL for a few years. I think I'm ready. So what I did is I just called up all my friends that I knew would work for free. And I said, hey, we're getting the band back together. Like, I want to go to the moon. And so all my friends that knew anything about the moon, some of them had left the field. Some of them were working in data science outfits. Some of them were working for defense contractors. Some of them were in academia, just all over the map. And I said, hey, you want to work on this moon project? And we started a Facebook group that was called like the Moon Shadow Council Facebook group. And so we just started talking about this idea. So here's the kind of steps, as far as I know them, being this story isn't finished yet, we're kind of halfway through, how to make your mission a reality. So first you have an idea, then you find some like-minded individuals that are extremely enthusiastic and willing to work for free. And then you kind of have to do some feasibility studies. Do you actually have a rover? Is it actually going to work? During our feasibility studies, we found out that the place that we were considering in the bottom of this pit is actually the hottest place ever discovered on the moon, which is very interesting scientifically, but the engineers don't like it. They're, oh, the hottest place that you could ever conceive of on the moon. That doesn't sound like a great place for a rover to go. And then we kind of had to win support from different key players, first of all being JPL. So we would go to the head of the mission formulation and we would say, hey, we want to talk to you about a mission. And it was pretty funny because at the time he was very focused on Enceladus and Europa. And so he would say, unless your robot's going to take me down an event in Enceladus, I don't want to talk to you. And so he kept pushing us off like, oh, come and see me in 3 months. I'm busy for the next 3 months. So we'd put a thing on his calendar in 3 months from then, and then go and see him. Oh, I'm too busy. See me 2 months from now. Finally, we got on his calendar and we said, listen, this is what we want to do. And over time, they really started to think, oh yeah, that would be really cool. I like that idea. So we're kind of selling it to the institution. And then the institution supported us for a proposal run. So we write, a 400-page proposal. We submit it to NASA, the big competition, try and win the discovery competition, which is the total amount of money, at least last time, was about $500 million that you could get. And so this is kind of how you do it. You submit it to NASA. Most of these go through the ringer, 3 or 4 times, maybe even 5 times. Some of the ones that are in right now are in their 4th or 5th try. And so then, okay, you come back, you try again, you find funding, you develop all your technologies, your rovers, your instruments, your science ideas, write a bunch of papers, and then submit it again, see what happens. So you can see this contest happens every 4 years. So you can kind of see how this could eventually take 30 years as it did for my friend. So here's the team that we put together. This is most of the science team, and then most of the engineering team. You can see the size of the Axel rover there and how scratched up it is from us testing it all the time. So these were the people crazy enough to sort of get in on this adventure with me. And I challenged them, okay, all we have to do, guys, is land right next to this pit, but not in it. We have to rappel off the lander. We have to rappel down 125 meters into an extremely dangerous pit with unstable walls, have to take a beautiful shot of the Earth from the bottom of the pit, which we actually think is possible. We calculated geometrically that we could see the Earth from the bottom. And then, okay, once we get to the bottom, explore. Someplace that's completely unknown. We have no idea what the rover will encounter. So while everyone was kind of focused on the tube, like, oh, we could put all this stuff in the tube and we could have a base there and, there might be aliens down there, all that stuff. The thing that really caught my attention was not the tube at all or the cave. It was this picture, which shows from an oblique angle all of the beautiful rocks that are exposed in the entrance to this pit. So I'm a geologist. I'm very interested in rocks. On the moon, there's almost no bare bedrock exposed, and here was a beautiful cross section, something like 60 to 100 meters of layers looking into the history of the moon. So the reason I find this very fascinating is the analogy I like to use is that geology on the Earth, they say it's like reading a history of the Earth, but with half the pages torn out. But it's really more like tear out half the pages, shred them into a million pieces, burn them and smash them, weave them into sedimentary rocks and new rocks, waterlog them, fold them into a bunch of, origami features, and then try and figure out what happened billions of years ago. It's very difficult. I used to study the early Earth, the Archean, and we'd maybe have like a couple zircons that we'd study and try and figure out everything that happened in this era just from a couple zircons that were left over. The moon is much more tantalizing body because it is a time capsule that is frozen from billions and billions of years ago. And really the only thing that happened after that was it was smashed into little bits. So you get like a shredded layer of rock that sits over the rock that you're looking for. So here's what it looks like, a shredded layer of books. These are from different Apollo missions. The ones on the bottom are from Apollo 15. And so you can see through this, it covers everything. It's really hard to find bedrock. There was 2 times when we approached bedrock. One was in Apollo 15 in Hadley Rill, which is this valley here that I'm showing you. This valley here. If you look across the rill on the other side, you could see layers exposed, which we thought could possibly be bedrock, but they're very far away and the astronauts couldn't get to them. And then the other very tantalizing spot was we think we passed a little bit of bedrock exposure with Lunokhod 2, which was the robotic Russian rovers. But Lunokhod 2, their main goal was just driving as far as possible. And every day in the Russian newspaper, they would publish how far they'd gotten in any particular day. And so they didn't want to take a lot of time to stop and look at this stuff as they were going. Really, science wasn't their main goal. So that's a huge loss. So this particular bedrock exposure is super exciting to me because how this is made is you have some kind of tube, or it can be a fault or fracture that's way deep in the surface. And then it's not like a skylight where you get a hole in the ceiling of that tube and you can see active lava pouring through. It's really, you have a tube or a void in the subsurface, and then over millions or perhaps billions of years, you build up lava layers over that void. And then at the very top of that, when the lava stops, you get regolith formation. So you're smashing up all of the lava and kind of mixing it together. And then the last thing that happens is that the ceiling of that void is weak, and it starts to collapse from right above the lava tube, and then keeps collapsing upward, upward, upward until the void finally reaches the surface. And then it's a collapse tube. And so what you find exposed in that hole are really pristine rocks that have never been messed with. They don't have a crater running into them. They're not shocked by anything that happens. It's really a clear cut and a pretty fresh cut into the history of those rocks. And so what we like to think about this is, you know, we're sitting with the regolith down on top, and then all of these layers are like, it's so much easier. You just have to read the book. You don't have to piece it together from a million puzzle pieces. So what do we care about looking at lava layers? The reason that we care about it so much, especially on the moon, is because the moon shows us a time in planetary evolution that we don't get to see almost anywhere else. So when you make a crust, first you have accretion and all of the bombardment hitting the planet, and then you have a global magma ocean, maybe everything's super hot. And then you get the first crust that ever forms. And on the moon, it was a flotation crust where all the light, low density minerals floated to the top and made the first crust that was on the moon. And then what usually happens is you have volcanism from deep inside the planet, and it resurfaces the whole planet. And that's what you see on Mars. The whole planet of Mars is covered in basalt. Basalt is the kind of rock that comes from deep in the mantle. What happened on the moon is that it had its primary crust, which is the, you know, light and north acidic part of the moon. And then it started becoming a secondary crust, and it stopped. So we can see it's frozen in time right in the process of forming that first secondary crust. And so we can see both what comes out of the moon and sort of reconstruct what the inside looks like, but then also what did that crust come up through? So you can get the entire process of how the secondary crust formation happened. If you look on Mars, that has already happened. It's totally covered in basalt. If you look on the Earth, not only did it get totally covered with the secondary crust from melting the interior mantle, but it happened many times where you had plate tectonics and things were diving down into the mantle and then they're melting again. And so you get both basaltic ocean floors and the continental crust. So that's kind of, we think there might be some tertiary crust on Venus, but really most of the planets in the solar system are showing the secondary crust. And so the moon is a really good example. Maybe Mercury, we haven't figured that one out yet. A really good example to look at how that process happens. So this is how the moon's crust was formed. First, you have that magma ocean I was talking about, and then you get all of the light, low density minerals, really bright white. You know, that's why the moon, the highlands of the moon look so white. They float to the top. All of the dark and dense minerals sink to the bottom, including olivines and pyroxenes. And then you slowly solidify the whole moon. And then you have melting events that bring like as if you stick a probe down into the moon and suck out little pieces from different levels and put them all over the surface. That's what volcanoes do. And so we have a chance to reconstruct both the sort of process of secondary crust formation, and then also what does the interior of the moon look like if we just piece it together from all the little volcanoes that we found. It also tells us something about how planets lose heat. So the Earth is this example where it has plate tectonics, things are diving into the Earth, you know, the mid-ocean ridge is opening. It loses heat really effectively because it can bring lava to the surface pretty easily. It has spots in its crust that are really thin. Whereas on the other planets, you don't have any plates. So the lava has to get through the plate somehow. It's sometimes difficult for it to get through the plate. And so it builds up a lot of pressure underneath the plate and then erupts kind of catastrophically. So on the moon, we have, or sorry, on Mars, we have big lavas that cover the whole like northern plains areas and kind of over here. And then we have these big, huge volcanoes like Olympus Mons that are right over like a long-lived plume. And then on Venus, what we seem to have is that whatever was building, this volcanism was building for a long, long, long time, and then catastrophically erupted, resurfaced almost the whole planet about 500 billion years ago. And so this kind of heat loss mechanism is the most common type in the solar system, the one plate planet, but it's not the one that's best studied, because the one that's best studied is the one that's the Earth, because it's very accessible to us. The other thing that's interesting about this kind of volcanism is that volcanism, people think about it as a destructive thing, that, you know, it's killing people and it's causing mass mayhem and stuff like that. But it's actually, I call it a creator of habitable worlds, because when you have your first atmosphere, when you form right after accretion, then it's mostly hydrogen and helium. You lose it in space pretty quickly. You wouldn't have an atmosphere unless you were replenishing it from interior sources and sometimes exterior sources. So you have a bunch of volcanoes erupting, they erupt water, CO2, they kind of reform like what the atmosphere of the Earth is today, nitrogen, all of that kind of stuff. That's forming the atmosphere that we have and making it possible for life to exist. Now on the Earth, almost everybody that has an atmosphere in the solar system has a secondary atmosphere. On the Earth, we actually have a tertiary atmosphere because life has messed so much with the atmosphere that we have by creating free oxygen, et cetera, that it's really not quite recognizable from what Earth's original secondary atmosphere would be. So if you have volcanoes that erupt very slowly over time, that's the best way, because you're slowly replenishing the atmosphere kind of at the same rate as you're losing it to space and losing it to minerals. And so you keep a steady state and then things can live there. Of course, volcanism has this other side of itself, which is depending on the flux of the volcano, it can also be a destroyer of habitable worlds. So if you look at through geologic history at all the many of the mass extinctions that took place, what this particular graphic shows is these peaks, the gray peaks are mass extinctions showing the percent of genera going extinct. And all of these red lines are the flood basalt events. So enormous volcanic activity, flood basalts pouring over the surface, and then you get a lot of these are correlated with a big mass extinction event. And the biggest one that we know about is the Siberian traps. Huge, it's probably, I think the amount of basalt here, they said could cover all of Europe in a basalt layer 4 feet thick or something. And so it's just basalt after basalt across the top of Siberia here. And that corresponds with the end Permian extinction 250 million years ago, in which, you know, some 96% of all species in the ocean went extinct. And that was caused by huge influx of CO2, sort of acidification of the oceans, and a lot of bad things happening with, with regard to the Siberian traps. Of course, the other famous one is the Deccan traps in India. And everyone always talks about the asteroid that killed the dinosaurs. And then there's this constant battle in the literature between the people that say, well, you know what also happened right at this time was an enormous volcanic eruption of the Deccan traps, which would have made the environment very hostile to life. And so I think kind of people are of the mind now, at first they thought maybe the asteroid hit and then it triggered this basaltic eruption to happen, which would make sense. But they've kind of determined that the volcanic eruption started happening before the asteroid hit. And so now they're kind of like, wow, I guess the dinosaurs were just extremely unlucky that they, if they could have survived one, then they probably couldn't have survived both of them at the same time. And so I like to say that if someone on a street corner is telling you that the world is going to end in fire and brimstone, you should probably know that it already has, and it's happened several times, and it definitely will happen again at some point. But hopefully we have several millions to hundreds of millions of years before that happens. And we can have a space program that can take us to multiple planets so that we won't be too vulnerable. So if we look towards the other planets as a hint of what is important, how important this process is, what we find is that 40% of Mars is covered in these sort of large, enormous flood basalts. 60% of Venus is covered in these flood basalts. Most of the rest of Venus is covered in regular plains volcanism, so almost the entire Venus is covered in some kind of volcanoes. On the Earth, we only find about 7% of the surface covered in flood basalts, but that's really because the Earth's surface is so young and it's constantly recycling itself. So any flood basalts of the past have been subducted, they've been covered up with something else, so we don't see them. On the moon, about 17% of the moon is covered in flood basalts. So like I said, it was this case where the secondary crust kind of started to be created and then just stopped. And so we can see it right where it stopped. And then Mercury, really, we hadn't looked at Mercury up close since 1973. And then I was very lucky to be a graduate student on the Mercury Messenger team in 2009 when we flew by Mercury again. And at that time, we didn't know if there was any volcanism on Mercury at all. But since 2009, we have discovered that about 17%, kind of similar to the moon, of Mercury is also covered in these enormous flood basalts. So it's a very common solar system process, even though we don't think about it that much on Earth, because the last time it happened was about, I think it was 15 million years ago was the last time we had one of these events. And even that one 15 million years ago wasn't a big one. So it affects planets in different ways. For example, some of the largest flood basalts on Mars happened in the Hesperian period, which was from 3.7 billion years ago to about 3 billion years ago. And that was right during the time period when, during the Noachian, they call it that because it's like Noah, and there was floods and there was lakes and rivers and possibly oceans on Mars. And then there was huge giant eruptions, lots of bad things happen, 30% of the surface gets covered in basalts. And then it's not like nice to live on Mars ever again. So we're still digging into how that happened and to what extent the flood basalts are responsible versus other things like the loss of the magnetic field, the loss of the atmosphere, et cetera. And then on Venus, of course, it's very obvious that it had a huge effect, the global resurfacing of the planet. One thing that we don't know that we're investigating is what kind of effect that sort of global resurfacing would have on Venus's atmosphere, because Venus's atmosphere is absolutely extremely dense, full of these volcanic gases, full of sulfur dioxide, and it would be a catastrophic thing to happen. Whatever Venus could have been nice before that, it definitely wasn't nice after that. But then, so the thing that we're really after is how the flood volcanism happens. We know on Earth, some of our flood basalt provinces are better studied than others. One of the best studied flood basalt provinces is in Washington State, Washington and Oregon. And so they have enormous flood basalts there, Snake River, if you've ever been in that area. And people study those a lot because they're really easy to get to. And they found that at first they thought, wow, we think that these, you can see these cars here. This is just one lava flow, this entire thing. And so they're very, very thick. And people started thinking, like, how can a giant thick lava flow like that flow across the surface? In the case of the Columbia River basalts, it could flow for something like 400 kilometers and reach the ocean, and it's still warm. So was it flowing turbulently across the surface like flood? Or was it flowing kind of slowly across the surface, but insulating itself with a lid, kind of like a lava tube? And what they found over time is they think it's the latter, that you have a pretty thin lava layer, and then it grows into a big thick lava layer, and then the lava goes through it like crazy. It's got like a lid on the top and on the bottom that's insulating it, and then that's how you get all the lava through it. And then you have incremental volcanism, which is more like the kind that you see in Hawaii, where you just get a little bit of volcanism coming out, over the scale of hundreds of years. And the volcano that's happening in Iceland right now is kind of like that as well. But then the more mysterious answer is there any such thing as turbulent volcanism? So I was saying some people thought in the beginning, oh, these lava flows, they go really fast like a raging river. Are there any such lava flows that are like that? And when we look towards the planets, we see some things that suggest that they might be. For example, on Mare Imbrium, just kind of similar to the Columbia River basalts, we have lava flows that go on for maybe 600 kilometers, which is extremely long for a lava flow. And then we see these enormous basins, and they're just covered in plains. They're kind of boring because you don't even see a volcano there. It's just a vast plain completely covered in hundreds of meters of lava, and you can't even tell where it came from most of the time. This is a very unusual feature that's on Venus. It looks like a river, and if you saw it on any other planet like Mars, you'd think, oh, okay, that was formed by water. We know that there was no water on Venus because it's much too hot, and so we have to come to the conclusion that there was some kind of extremely fluid water-like lava that carved these channels. And we find similar channels on Mercury and on Mars, and we find similar channels on the moon as well, these sinuous rills that people are constantly arguing over whether or not whatever lava went through that sinuous rill, if it could actually erode it like a river instead of just depositing things like we normally imagine lava doing. And so it leads us to this idea that maybe what's happening on the planet is more extreme and more bizarre than what we have seen so far happening on the Earth. And more like the closest thing we can think of that's similar is that back in the Earth many years, billions of years ago in the Archean, there's some lavas that suggest they have the composition such that if you melted them to normal lava temperatures, they would flow very fluidly. And so it could be that it was just in the Earth's very early times that it acted like the other planets. Now it's got its own thing going on, and all the other planets are still acting like that. The moon is kind of the most extreme example because it has this flotation crust I was talking about. It's low density. And if you're trying to get a high density lava, even though it's warm, the warmness makes it more buoyant, but it's hard to get that lava actually through that low density crust. And so you build up tons of pressure below the crust. And then once you finally crack through the crust and you get the lava coming, it's going to come out super fast like crazy. So that kind of makes sense to us. But this flux would be very important for whether or not it has an effect on the atmosphere, not only on the atmosphere of the Earth, where if you have an enormous flux, you get mass extinctions. On Mars, if you have an enormous flux, you might be able to shut down Mars's hydrosphere. If you're on the moon, you have an enormous flux, you might actually form an atmosphere that currently doesn't exist. So if you're just pumping volcanic gases into the moon's exosphere, you could potentially, a friend of mine wrote this paper saying, if you did that in a short enough amount of time, then you could have a lunar atmosphere that could potentially, it would be about the thickness of the Martian atmosphere, but it would last for about 70,000 years, and then it would dissipate, which is really weird to think about. So all of these things, what are the flux of this basalt? It kind of touches a lot of parts of planetary science, because if you say, oh, these are common across the planets, and if you do find they erupted some outrageous flux, then whether Mercury ever had an atmosphere, whether volcanic sulfur was key to cooling down the ancient surface of Mars, all of this water that we've been talking about that's located at the poles of the moon, where did the water come from? Could it have been volcanic water that's accumulated there? All of these things sort of touch across many fields. The other very interesting thing about looking at a big stack of basalts is that you get to look at each individual rock and figure out where it came from inside the moon. And it helps you sort of back calculate what the interior of the moon actually looks like. And since we know that the interior of the moon, it formed, it was starting to differentiate. We don't know if it finished differentiating or if it just stopped, kind of frozen in time, like the formation of the secondary crust. And so we're trying to figure that out. And so I like to think, like, if you start studying petrology, which is the study of rocks and where they came from. So petrology, every rock is kind of like a human being, where it's how it is right now is a combination of where it came from and what's happened to it since then. So if it comes from deep in the mantle, it's got a certain composition and a certain set of minerals, and then it makes its way through the crust and it interacts with different crustal materials, and it mixes with other lavas, whatever. It goes to college, it gets new ideas and whatever. And then it gets to the surface and erupts as lava. And then maybe as it's cooling, other things happen to it. And so when you just find a random piece of rock on the surface, it's actually really hard to figure out, like, okay, where in the lava flow did this come from? How much of what I'm seeing right now is a result of how it was brought to where it is now versus where it came from. And if you get to look at a lava that's actually in cross section and it's in place, then you can figure that out a lot easier. You can see on this rock here, this is an Apollo rock. It has some crystals. Let's see, these are like green crystals, and these are vesicles, which are just from volcanic gases that came out of the lava as it was flowing on the surface of the moon. So you can really learn about how much gas was in this lava and where did it come from and what crystals were stable in this thing. And then you can track it back to where it came from in the mantle. And if you get enough examples of those, then you can kind of piece together what the inside of the moon looks like. So this is, coming back to this idea. Oh yeah, and then the last part really is the knowledge that almost everywhere else you look on the moon that's not in a beautifully exposed hole is going to be covered in regolith. And so you can kind of look at, oh, I've got a big stack of lavas down below. How many of those are represented in the surface regolith? So if all I had was regolith to look at from now on, which is the case because I don't have this many holes, what would I be able to still learn about the moon now that we have this, this sort of a ground truth testing point? So the instruments that Moondiver uses to figure out these problems are, there's three of them. There's a camera system, which includes stereo cameras. The rover actually uses it to navigate as well, but it takes stereo images of the lavas as it goes down. And there's one camera to look across the other side of the pit, and it measures the thickness of the lavas. And then it measures their morphology. So we can figure out if it's an incremental type of lava, if it's an inflated type of lava, or if it's this crazy turbulent type of lava that we're not even sure exists. And so we use cameras for that. And then we have a microscopic multispectral imager, and that looks way up close at the rocks and figures out, oh, what minerals are in here? What do the vesicles look like? Really, really up close. And then we have an alpha particle X-ray spectrometer, and that tells us the chemistry of the rock. And so with the chemistry and the mineralogy, we can figure out where did this come from inside the lunar mantle, which is really exciting. And then we had a bunch of ideas for additional payloads we could put on it. So at the end, you have like $500 million. It all goes much quicker than you would imagine. And then at the end, they say like, hey, if you had an extra $20 million, what would you spend that on? What we wanted to make spend that on is a package of instruments that we would use to actually explore the tube, like a LiDAR and flashlights and things that we could do. It's, it's the end of the mission. You don't know what the terrain is like. You could drive in there and get stuck, or you could drive in there and a rock would fall on you or something. It's kind of the dangerous exploration part of the mission. But we could do that, and we could sort of map out the size of that cave in case anyone really does want to live there in the future. So the moon is really ideal for this because it's just so simple. If you think of all the each planet is a different laboratory experiment. But you weren't the ones that got to choose the starting conditions. So the Earth is the absolutely most complicated laboratory experiment you can imagine. The moon is one of the most simple. There's no plate tectonics. There's no weathering by wind or water like there is on Mars. It's right next door, easy to get to. Great amount of solar energy for solar power. You can land a lot of stuff there because you don't have to go that far. And then there's low latency between you and the Earth. So it's only 2.5 seconds round trip to the moon. So you can talk to your robot and kind of command it. Here is some example of all the different pits that they have on the moon so far. They do have, I think, up to 17 to 20 pits. My colleague, Robert Wagner at ASU, is the one that's mapping all of these pits. And he finds, a couple more every every 6 months or so. And then at the bottom here is a bunch of pictures of that Tranquillitatis pit, so you can see it from different angles. One of my favorite pits is actually on the far side of the moon, Mare Angini. It has a lunar swirl that's right next to it. And then this giant pit in there, beautiful stair step layers, much easier for a rover to rove down than a totally vertical or overhung pit. Here's the location of the Tranquillitatis pit, which is our ideal pit to go to with Moondiver. It's on the front side, so you don't need a communications relay, and it's got a very nice exposure of layers of a very interesting rock type, because they're the same rocks that we actually picked up on Apollo 17 and Apollo 11. It's kind of halfway between them. So what are the challenges that the mission faces from an engineering perspective? It is extremely hot inside the pit, 120 degrees Celsius. That's actually on the surface. And then the nighttime is so cold that it's really hard for us to guarantee that we're going to survive unless we send along some sort of radioisotope power. And we usually don't want to send those along because it's very expensive to get launch approval for those sorts of things. And so what we decided to do is figure out, can we do this entire mission within the span of 1 lunar day, 14 Earth days? So you have this limited time, and then you have the dangerous dust. The regolith is sharp and powdery. It gets into everything. You have to protect your instruments from it. You have to protect your tether from it that you're hanging down. And then of course, the ultimate challenge is just rappelling down a giant moon cliff into a mysterious cavern where you've never been before and you have no idea what's down there. So in order to prepare for such an adventure, we've been doing a lot of testing. Here's the Axel rover at JPL, and we built this wall for it, which was just, I took my intern, I said, hey, intern, you want to go on a fun adventure? And I said, I'm going to go out into the Mojave Desert. It's 105 degrees right now, and I'm going to collect like hundreds, like probably 500 pounds of rocks and put them in my car. Do you want to help me with that? And he was very enthusiastic. So we went out there in 105 degree heat, and we loaded my entire Forerunner, filled to the top with basaltic rocks. And then we kind of glued them and bolted them onto this surface so that the Axel rover could actually look at real rocks with its instruments as it was, practicing going up and down. Then we took the Axel rover out into the field, and we in Arizona, and we did a field test there. This is a field test we did in California where we actually rappelled it down. It actually broke. We had to manually grab it and bring it all the way back to the top. Just, you gotta have strong people on your team, And so here's the tether team. This is Patrick McGarry, is the tether guy, and he was practicing basically putting the tether through every sorts of terrible thing you could imagine. This tether is actually only about, I would say about 8 millimeters thick. So it's really crazy. It can hold an enormous amount of weight. And then we were practicing with our instruments. Here's us on some of our other field tests. There's our tether being tested across the sharp rock. And we actually built a lander facsimile and then tried to repel the rover off the lander, assuming the lander landed at some crazy angle, just to prove that we could do it. And here's me actually in a tiny lava tube in the Mojave Desert. And then there's the other half of it, which is figuring out, is it actually going to work from an engineering perspective? And then the other half of it is convincing everyone else it's a good idea. So, and explaining to them how it works in a coherent fashion. So we actually made all these little 3D printed keychains, and they would come out like one of those things you attach your wallet to. And so we'd give it to people at conferences so that they could kind of see how Axel worked. It had all the degrees of freedom that Axel had. And then we made, this is a moon cave cake. And so as you can see, if you cut into the cake, you see not only the cave here at the bottom, but you can also expose all of the beautiful layers of rocks and the totally smashed up version of those rocks that is on the surface of the cake. The operations part of Moondiver is also a really big challenge. This is a picture of the Russians operating Lunokhod. in the 1970s, and they actually had a team of 5 guys, and they're basically joysticking Lunokhod across the surface. It's like playing a video game with extremely terrible lag. They just had to sit there, and every 2.5 seconds, I think they had a frequency of about 3 seconds between images on Lunokhod 2, and they just had to kind of remember what rocks that they were about to hit so that they could proactively steer around them. It's a very intense situation. So I like to project into the future. I told JPL that I think I wanted this kind of setup for my control of Moondiver, so that whoever was the operator of the rover could sit in this mysterious underground cavern with a giant screen and just operate Moondiver from there. And so far they have said no. So in conclusion, Moondiver right now is a mission that does not exist officially, may never exist. But that's the way all the missions start. We've gotten a lot farther in the last 5 years than I ever imagined that we would get in 5 years. All the way from an idea to an actually proposed mission to NASA Discovery. It got to the final 19 missions, and then they brought it down to only 4 missions, and we didn't make it to that step. In just a couple days, probably at the end of May or the beginning of June, they're going to announce the winner of this particular contest between the 4 that remain. So stay tuned for that. That'll be very exciting. There's 2 Venus missions, a mission to Io, and a mission to the Neptunian moon of Triton. So we get another chance. We're going to get another chance. Our next submission is in 2023. And we've actually just been working just full out in the interim to mature all of our technologies, to learn more about our science questions, and to prepare our proposal for next time. If this does get to be a mission, which I hope it does, it would be the first mission to venture below the surface of another world, and the first extreme terrain mission. And it would be really interesting as an advanced scout for future human cave bases, going where no robot has gone before. So I kind of hope that even if it doesn't become a mission, that it will inspire people enough that somebody will go and take a look in one of these moon caves, because I think they're very fascinating. We have our next chance in 2023 to submit this. That would be for a flight that happens around 2029. But everything's changing at the moon. Things are going really quickly. You may have heard of Artemis. Artemis is, going like crazy steam train under the last administration. This administration is a little slower, but we were very gratified to see that they still support the Artemis mission. And so it's still going forward, and faster than anybody, I think, would have hoped. And then along with that, they're sending a bunch. They have this commercial lunar payload services where they're kind of paying on contract people to build lunar landers, and they're all supposed to go this year. They're supposed to go every 6 months for robotic landings, and then they'll get to the human landings as well. And so there's actually ends up being a lot of avenues for Moondiver to go through besides just the traditional avenue, which is a competition against all the other bodies in the solar system. There's also just a lot of money and interest in the moon right now. So we're very excited about where the future of the moon is going, and we hope that Moondiver can participate in some way. So with that, I will end. I think I went a bit long perhaps, but I stick around and take any questions that you have. And thank you very much.
Thank you
Thank you,
very
Laura.
much, Laura.
Thank
Dave
you.
Hockenberry here.
Very
A
cool.
question I have for you as a geologist. One of the things that I would think that this technology that you've been looking into would address is, how did the moon form? There are competing theories about it: the capture theory, co-accretion, fission, and of course the giant impact, which is currently in favor. As a geologist, what would you expect to see with these instruments? What evidence would you be looking for in a project like yours that might help to sort out how the moon formed?
Well, there's a couple things. This mission is focused on kind of the next step after it forms, and then we assume it melted to some enormous depth, and then it's now forming a secondary crust. That's kind of what it's focused on. But if you go back, some of the things that we think about when we're talking about the formation of the moon is like, how many volatile elements do we find inside the moon? And at first, we really didn't find any volatile elements. We thought, wow, the moon has hardly any sodium. It's got hardly any water. It's very, very dry. And so that must have been some enormous amount of energy to drive off all of those volatile elements. But in the more recent times, in the last 10 to 15 years, people have been looking up close at some of the lava rocks and the pyroclastic deposits on the moon and finding that they have a lot more water than we thought they originally did. And so this was a challenge to the giant impact model, because they had geared all of their models to explain the fact that we didn't have very much volatile. and suddenly they had to say, oh no, wait. If a giant impact hits the Earth and the moon, it drives off all the volatiles, yes, but some of them can reaccrete. And so that explains why we can still get a certain amount of volatile elements inside these lavas that we see. And so that kind of thing would be something that we could look at. The other stuff, you'd kind of almost need to work in tandem with other missions. Like the big mission that everyone's quite excited about is they want to send a network of seismometers to the moon. And so they put seismometers all over the moon, and then they try and figure out to what depth the moon actually melted by kind of sending waves through it and seeing where the internal like mineralogy changes. So if Moondiver we have like a set of aliquots or samples that we've taken from the inside of the moon at different depths that show up in these layers. And then we could compare that to the seismic readings and sort of compare them to where we think they come from. Then we could not know a lot more about to what depths the moon melted and to how much it mixed afterwards and stuff like that. And that puts an endpoint to all of the models that we need to model its actual formation. So it's kind of like a two-step process that you get back to the formation of the moon.
Thank
Hey
you very
Laura,
much.
Peter LaFrance here. On the two-wheel rover, it has a tether coming out of the tube, I think.
Yep.
How steep can that go?
How steep?
Yes.
Yes, it can hang there. Like in this picture here, it's just hanging.
So why
So
have wheels? Why not just a regular camera?
if you're on a slope that's less steep than vertical, then you need the wheels to go across.
Okay, so you're not
But-
sure how steep it is.
Well, we're sure that it's both of those things. We know that at the very top of the hole, it's not quite vertical, it's less than vertical, so you'd be kind of rolling along on your wheels. Plus, before you get into the hole, from the lander to the
Gotcha.
hole, and then once you get down far enough, there's a big old overhang, and at that point, you're just hanging.
Okay, thank you.
So this is John Conrad, Dr. Kerber. Like this picture shows here, your explanation of how these pits form. Can you hear me all right?
Yep.
Okay, your explanation, if I understand it, is that these lava tubes have formed and the layers of the moon pile up on top of it successively. And then at some point, essentially the roof of the lava tube collapses and everything above it just successively collapses to the surface. So you get like chimneying. Is that right?
That's right, yeah. Yep.
So what I don't, and I've understood in the last few years I've read about this, that, I mean, that's a theory, it's not known. Are there other ideas? Because it kind of mystifies me. I mean, lava tubes are not just spheres down there. They run laterally. And so if
Yep.
the roof's going to cave in, why don't you see the holes at the top rather than to be mostly spherical and in some cases remarkably, I shouldn't say spherical, but circular, remarkably circular, as opposed to channels, if you will. And
Yeah,
are there
well-
other theories other than lava tubes for what have caused these circular pits?
Yes. So basically, in order to get these sorts of pits, all you need is some sort of void in the subsurface. And that can also be, it can be a lava tube, but it can also be like a graben or a fault or even a dike of lava that's a magma that's kind of rising to the surface. But to address all of those things that I just mentioned are linear. And so it is always a question in people's minds, why don't we get oblong pits? The answer is we actually do. So in places like Mars, you can find at the top of a graben or at the top of what appears to be a dike, extending out from that, you have the graben structure that you can see. But within the graben, where you start to get pits, you get a chain of pits. And some are circular and some are oblong. And so in those situations, it's very clear what's going on. You're saying, okay, there's something that's pulling apart. And then the first thing that happens is you get these little collapse pits. And then as they pull apart long enough, they become oblong and then they join each other. And then eventually what you get is just a big trough. That's what the end state is. So when you see a pit all by itself, it's quite hard for us to say for certain what structure lies below it, because it's all we see is the one. The pit that I showed you in Hawaii with my friend in yellow shirt, that's an example of there's a big fracture running underneath, kind of through the Kilauea volcano. And then all along the fracture, you get almost completely circular pits. It's actually crazy, but you get some that are oblong. And if you do the experiment yourself, kind of putting like a sand layer and then removing support from underneath it, you'll find that little round pits form first, and then eventually they coalesce. It's just kind of hard to visualize, especially when you have one that's all by itself. There's another one on the moon called the Marius Hills pit, and that's actually sitting right in the middle of like a sinuous rill kind of graben structure. So that one you're like, oh, okay, I can see that this is a linear structure. This one in Tranquillità is all by itself, so it's harder to link to like for sure what kind of structures underneath it causing the collapse.
Thank you.
Laura, this is Bruce. Great talk, really, really great. I'm just wondering, when you tried to conceive of the design and you were working through some of the engineering aspects, did you ever consider this type of mission, not just for the moon, but for Mars? I mean, there are lava pits and lava tubes on Mars. Have you ever floated that idea? Would it have maybe a greater chance of getting funded, given rising interest in Mars? That's first question. And the second question, this may be naive, I'm assuming that this is an unmanned robotic type mission, but if you have Artemis and follow-on missions to the moon, and you have in the 2030s missions to Mars, and you're going to have rovers, couldn't these be an accompaniment to manned missions where you would have much better control? I mean, it would just be part of your toolbox essentially to investigate the lunar or the Martian surface, or subsurface in this case. So have you floated any of those ideas or thought of those ideas, or were they not really viable?
Yeah, no, you're exactly on target there, because on Mars there's tons of pits and caves. There's the additional allure that a lot of those caves could have ice inside of them. Right. And so if it's just cold enough inside that cave, and it depends on the latitude, you could have ice inside the caves. You could have preserved evidence of past climate, like we see in a lot of caves on Earth. You could have life inside of the cave because it's protected. It's like a refuge protected from the hostile surface environment that has all the UV rays and things that life doesn't like. So I have a colleague, Charity Phillips Lander, and she's really focused. I want to go to Martian cave and I want to do an astrobiology mission. And so the way we view Moondiver is that there's a lot of easier things about going to the moon, that you have a much lower delay time when you give your commands, and you don't have to have an aeroshell, and it's a lot more expensive to go to Mars and land on Mars. So we view ourselves as a pathfinder, that if you proved it out on the moon, then people wouldn't think it was so crazy that you couldn't then do it on Mars. So that's the Mars part. The part about the astronauts, this Axel rover, that the way that ESA envisioned it is really a multifunctional thing. Like, Axel rover is the size that it is because the instruments that I wanted to put out on it are the size that they are, and the lavas are the size that they are. So it has to be able to go over them, and you have to put radiators on all this stuff. but it could be any size you want. And so he had ideas like, oh, if you had a rover like Mars 2020, you could have this as like the little side bot that if Mars 2020 wanted to stop at the edge of a crater, go over the cliff edge and take some measurements or something, it could do that and then just come back. He has a version of it where it's kind of two of them and they click together and then they rove around like a four-wheeled rover. And then when they get to an interesting thing, they disconnect. And we tested it out in the Mojave, which is really cool. You can find a video he made online. But then you can use it also for an astronaut. Like you could have a little tiny version like the size of a cat. Astronaut just wants to know what's in Hadley Rill, but it's too dangerous to go down there. You can just kind of throw it over the side. It could take pictures for you or collect samples. It's just like you said, it could be a tool in the toolbox. If you're in the North or the South Pole and you wanted to go into a permanently shadowed crater, but you can't because you're a human being and it's too cold, just send the rover in there to get some samples for you.
Great. Thank you. Thank you.
Hey, Laura, this is Chris. I got a couple of questions too. You show like the picture that's up right now. Would this Axel rover have lights on it that you would be able to illuminate an area to see what's in there?
Yeah, so we did a lot of studies to try and figure out how bright a light we would need in order to do that. And at first, if you're right towards the end of the day and you have light that's shining in the cave, we figured the first maybe 100 meters, we could just take a really long exposure and then we could see what's in there. But ultimately, if you're actually roving into the darkness, you'll need a light. And so we kind of had, it was more like a flash that would just, every time we took a picture would flash. And so you wouldn't have to put so much power into the light. It would be like a capacitor. But then the other idea we had is to use a LiDAR. So no matter how dark it was, you could still navigate.
Okay, and my other question was talking about Perseverance a little bit on Mars. There were some photos of some of the rocks that Perseverance has seen that look very similar to the one that you showed that had some, looks like Swiss cheese, I guess you could call it, with holes in it. Have you had a chance to look at any of those? Do they appear to be lava to you, or what do you think?
Well, this is a very funny question because one of my friends is the deputy project scientist on Mars 2020, and they've just been arguing about it kind of nonstop since they landed because they haven't had a chance to bring out their whole suite of instruments yet to examine the rocks. So they just have the pictures and they're just like arguing ad nauseum, like, what are those holes? What are these holy rocks, as they call them? I think that they're vesicular basalt lavas, just like the one I showed you, but I'm a volcanologist. So of course, when I say that, they go, oh, of course you would say that. That's because you're a volcanologist. But it's also what we find on most other places we land on Mars too. So I think that they are, I will put my token on the board and say, I think that they are basalts with vesicles, just like you said. Other things that they could be is like if they're a sedimentary rock with concretions, like we found at the Opportunity landing site, the blueberries. And then the concretions weather out, then they can leave holes like that. But for me, it's just like, yeah, come on, it's a volcanic rock.
Thank you.
Would the vehicle be driven from Earth or would it be autonomous?
It would be driven from Earth, but a lot of what ESA NESNIS does is autonomy. And so parts of it would be autonomous, like it would sense the surroundings, it creates a map of where it's going based on structure for motion. And then it could, ideally, the software that he's working on could at least suggest paths, and or if it was in a particular precarious situation, it could move itself to a more a safe situation. But just honestly, it's a cost thing. We're on the moon and we can drive it, so we might as well, instead of paying lots of money to come up with algorithms so that it can drive itself. Make it bigger. If we did go to Mars, we would have to do that. So that's the other complication that you add when you add in Mars. It's just the time delay.
How do you anchor the lander into the moon's surface?
Oh, we had to do a study about that because we were kind of afraid that we would topple the lander over if you're pulling on it too much. But as it turns out, we have these kind of disc-like legs. And then the lander itself is very heavy because it has all the fuel tanks and the solar panels and antenna dishes. That's actually the part that communicates back home and provides power. So it's heavy enough. When we compared it to the tug that it would get from the Axle rover, it's not going to move.
So does the rover get its power through the tether?
Yeah, it gets both power and communications through the tether, which allows it to be totally independent. It can go in darkness, it can go in light, it can be under a rock, and it still can communicate to the surface, which is convenient.
And how long of a tether can you have?
Yeah, I was just going to ask that.
Oh yeah, so right now our tether, I think, is about 300 meters long, but it can be up to probably a half a kilometer before we really get problems with like power losses across the tether. That's the real limitation. Like the tether is so tiny. I was telling you, it's like 5 or 8 millimeters, and it's got different sheets of different material, like a strong material, a strength member, communications, etc. And so you can fit tons of it on that winch that in the middle of the axle rover. But then at some point, if you're bringing power across the tether, you have to bring it to a really high voltage in order to bring it across such a long distance, and that's kind of the limiting factor. So we just have to land our lander within like 100 meters of the pit, and we demonstrated on Perseverance this kind of software that we're building, which is the precision landing software. And then on the moon, it's a lot easier because there's no parachute phase, no wind. There's a lot less uncertainty on the moon. And so we think we can land definitely within about 30-meter circle, probably better than that. And then we have plenty of tether to go into the hole, down to the bottom, and then some, maybe 100 meters back into whatever cave might exist. We know already that the cave is about at least 20 meters deep.
Very cool.
My wife has a question that she's hesitant to ask, so I'll ask it for her. Have any enterprising Hollywood producers, seeing these pictures, approached you about perhaps using your prototypes as a prop in a science fiction movie?
Great question.
That is a great question. Actually, I remember I was writing the listserv at JPL at one point, and I said, hey, does anyone know how to retrofit a GoPro so that it can go to space? And I forget the second question I asked, and I was like, and does anyone know James Cameron? And within like probably 10 minutes, I had the answer to all of my questions. And so it was like a 2-degree separation from James Cameron, because
Wow.
he has been he's part of the proposal team for a camera on Mars 2020, actually. And he's very interested in space, and he comes and visits us all the time. So I was thinking, if I can get him to contribute a payload or something, or make a movie about, he has millions of dollars. Like if he wants to put like a 16K, camera on there so that we can make a Moondiver virtual reality experience, like I'm fine with that. So the answer is no, but I'm accepting offers.
Thank you very much.
Yeah.
This has been very entertaining and very informative. You're a very entertaining speaker.
Yes.
I hope I live long enough to see your project come to fruition.
I hope so too.
Hear, hear.
Yeah. Thank you so much, Laura. Thank you tremendously for a great talk, fielding these questions. We wish you all the best with this. It's fantastic.
Good luck.
Thank you. Yeah.
Oh, there we go.
Okay.
Yes,
It was great. Really great.
Fantastic talk.
nice, very nice, yes.
Bye,
very
Laura. Thank you.
enjoyable.
Yeah, outstanding.
Bye-bye.
Very good talk.
Great.
And we peaked out around 42 or 44, something around that. So we had quite a few on YouTube watching. So
Right.
it was good.
Well, do any of our department chairs have any announcements or anything they need to let us know before we sign off? Because this is our last official meeting of the academic year. And are there any dates or things that our membership needs to know about?
Are we going to meet during the summer? YouTube meet.
No plans right now.
YouTube, I mean Zoom meet.
Yeah, no plans right now. Next one was
Okay.
September, but
Okay.
Dave, I was going to suggest maybe we should have, if possible, an exec committee meeting. We hadn't had one for a while. I think it was pre-COVID, right?
Yeah, it was just before the quarantine went
All
into
right.
effect.
Yeah, maybe several of us could get together sometime. I don't know, could be July or June. Partly to meet and just to discuss things for next year, float a few ideas around, take any suggestions that members may have. Basically a standard meeting.
Yeah, it supposedly with restaurants opening up at the end of this month in early June, I think there's absolutely no reason that we can't get the exec committee together sometime in June or July and start hashing some stuff out for next year.
Right.
But to all of our members, I'd say during the summer, pay attention to your email, pay attention to the website, pay attention to our Facebook page, because as things come up on the summer and as things either do or do not open up, I'm sure that we're going to, if events start happening, we need to get the word out to everybody. And to members of other clubs who may be listening in, if you guys are doing something or you have events that are going on, we, of course, especially if they're observing events, would like to know about it.
Yeah.
And if we're invited to participate, I think that there are several of our members that would love to get in on it.
Yes.
So let's keep in touch and pay attention to the social media, and we will definitely be able to keep connected that way.
Great.
I don't know, I don't know whether this is how external entities will be affected, but the university is going full on in person in the fall. At least that's the plan as of now, barring some kind of setback.
Yeah, we are planning to, and we even have a reservation for our lecture room for the fall academic
Yay.
year.
Yeah.
So,
we're good
yeah,
for
we're
that.
planning on doing that. The plan is also to keep Zoom or YouTube so that our members that maybe can't make the meetings can still tune in. But no, we expect to be back in the Westchester campus in September.
Nice.
Of course, we'll keep everybody posted about those details, depending upon the situation as it evolves.
Right.
And Don, how about Cherry Springs? Is there tentative dates on that?
Yeah, August, I'll have to look at the dates, mid-August, and then back up mid-September.
Okay,
And then
so stay tuned, because I know you guys are probably just chomping at the bit as much as I am to get out to some dark skies and start capturing some photons.
And there's the York County Star Party in October also.
Okay,
For August.
One thing I'd like to bring up for long-range planning, August 1st will be an Atari's rocket launch from Wallops Island.
I knew you were going to say that.
Time-
I knew
pardon?
you were going to say that.
The time I don't know yet.
all right, thanks, Pete.
They
Sure.
scrubbed today.
There's actually in June 3 rocket launches in June, but they're smaller rockets. They aren't quite the big Ataris going up.
Oh, Pete, I thought you were going to go making time so you could go watch the launch of the James Webb Space Telescope down in, was it French Guiana or whatever it is?
I'd love to.
I thought it was going to be Florida. I was set.
Take your bike.
What are you going to do?
Road trip.
Well, Kathy, you said you wanted a road trip to New York. Why don't we do a road trip to watch the James Webb go up?
Yeah, we can do that.
There you
I'll
go.
drive the van.
You're gonna need more than a road.
We need more than a road. I'll drive the boat. How's that?
Well, while we're here, I would like to put out a special thanks to Bruce Ruggieri. He put together a fantastic
I will say so, yes.
group of speakers for this year. We've been
Very
bowled
nice.
over by practically every meeting that we've had. I don't know why we kept that bum that used to do your job on as long as we did, because you've done such a fantastic job. I would just like to put a shout out there to you for, again, for all your hard work and getting this incredible group of speakers together. I've learned so much this year. It's
Oh,
unbelievable.
great.
Great.
Yeah, thank you.
I hope it'll continue into the fall and winter.